was the formulation of the solution method. I have a special use case that I think is important that utilities are very interested in. And I will close with some open issues, okay? The future work that there are a lot of academics in this presentation. So I'll let you know what I think is important that you guys can tackle moving forward. Very fast. All the action today is moving into distribution. We have a lot of demand energy resources behind the meter and in front of the meter. They are growing in volume and size and very diverse resources actually. A lot of issues recently relate to local resiliency of the grid. So there is a lot of effort in several states in the country, New York, California, about migration to microgrids. So there are a lot of microgrid development, and one of the drivers for this is local resiliency. The DNOs, these are the distribution network owners. These are the distribution utilities. This could be the DSOs that operate the market, or the DSO could be a different company. It's not necessarily the DNO. So it's a major policy issue. I'll talk about this later, about running the market as a DNO or running the market as a third party. These are some basic DR resources behind the meter or in front of the meter. So I'm moving on. Why we have this over the last several years, this massive DR proliferation into our system. There are two types of market forces at play here. One is bottom-up approach. There is an adoption from customers. Customers want it. And we see that being in the trenches here, working with customers, they really want it in all levels, residential, commercial, industrial. They want to participate in wholesale markets, individually or through aggregators. As I mentioned, local resilience is a big ticket item. And we see a lot of efforts from cities and counties across the country. Actually, Europe actually takes the lead on this to explore synergies between different services. And a lot of this is driven by climate change. So we're moving into a renewable based energy system, which creates a lot of problems in the wholesale market because we have what we call zero marginal cost systems. The marginal cost of these renewables is zero. We didn't build wholesale markets for 20 years for this type of market design. So many of us are back on the drawing board, how we can redesign markets to clear all these assets when we have so many resources with zero marginal cost. There is also what we call the IoT revolution. Every sensor that is coming into the system close to the customer, from smart thermostats, load switches for hot water heaters. We see that now. They communicate with the cloud, they have connectivity. So there is the IoT revolution. The top-down policy objective, of course, we have all these policy objectives to decarbonize the grid. So there are market forces from both sides, bottom-up and top-down, that they are making DR proliferation a reality. And from technology perspective, we see also that the cost of technology is getting cheaper and cheaper. Now, there are different stages in the evolution of the grid as a result of this massive penetration of DRs. We are currently somewhere between the first and the second stage. We have a substantial DR adoption already in the existing system. We could get by not doing much into the existing system, not enhancing the infrastructure or changing the operational protocols or planning protocols. if the DR adoption is low, relatively low. But as we move to more massive penetration of DRs, then we're talking about the need for new. We have multi-directional flows. The grid is becoming kind of chaotic, a lot of volatility. We need new investments in the T&D system and new protocols for operating the system. Another major area there is that DRs create a lot of challenges, but also create a lot of opportunities. The third stage of development is the distributed markets. Once we have all this massive penetration of renewables, we are moving to what we call multi-tier hierarchical markets. And a major important market now are the distribution markets. In the distribution level, that we clear the markets to acquire market services. But those markets require, of course, a new regulatory framework, and I'll talk about this later. In the US, there is an intense debate going on between states and the federal government, because many states, and I think this issue will be resolved at the courts, many states don't want distribution assets at the edge of the grid to bypass distribution and go straight to wholesale markets that are being administered by the FERC. At the core of the model here is what we call the transactive energy model, which I see this is coming in the next 5 years. So we'll have a lot of peer-to-peer transactions as a separate market between DR aggregators. This will be on top of the distribution market I'll talk today, and on top of the wholesale markets. So this could be transactions behind the meter or in front of the meter from peer to peer. Now, if there is one slide I want to you to remember after this presentation is this slide. We're moving to what we call an integrated electricity system. Okay, at the top we have the classical wholesale markets in the transmission level. These are the market operators, the system operators that we have in this country. In Europe, we call them TSOs, transmission system operators. We operate those markets for more than 20 years now. We know how they work, and we keep building those markets. However, those markets need to be modified now to account for the emergence of DRs and for the emergence of what we call DSOs. These are distribution system operators that are below the T&D interface. They operate local markets. Our basic principle here is that the DSO markets will not be subjugated to the wholesale markets. It will be independent. There is an effort for many ISOs to expand in the distribution and take over the whole thing. I don't think it's going to happen. People who are in the distribution business know that there is a huge difference between transmission and distribution. Distribution networks are very different. They are unbalanced. They are three-phased. We don't have enough data. There are different problems in operations. We have different ancillary services. So it's not a portable model. We cannot take what we have in wholesale to apply to distribution. In addition, there are huge computing requirements to make this happen. At the end of the grid, we have the DR aggregators. Now, this concept of DR aggregators, something that we have been doing over the last 3-4 years, has been sanctioned by the FERC. I'll discuss in a minute about the new FERC order 2222. So DR aggregators, usually they will be located in distribution. They will aggregate resources in behind the meter or in front of the meter. It will submit those resources to solve grid problems in distribution or bypass distribution and go directly to the wholesale market. So the evolution of the IoT devices and all these new assets at the edge of the grid create what we call the energy demand cloud. we are in that business. We have all these gateways now. We aggregate capacity from home management systems, thermostats, hot water heaters, anything you plug in the wall that is smart. Now we have new assets like electric vehicles, smart appliances, and solar. All these now have connectivity, and we take it to the cloud, and we parse that demand into tiers, depending on the level of flexibility. So we may have price-sensitive load, or non-price sensitive load, or load that you activate only during emergencies, and you parse this total capacity based on their flexibility. The theory behind this is based on nonlinear price theory. Actually, Bob Wilson from Stanford got the Nobel Prize on auctions using those priority tranches, and we put prices in those priority tranches, and we offer it to markets to solve grid problems like ancillary services in wholesale markets. So that gives you an idea about what technology allows us to do today. Now, last month, mid of September, FERC came out with Order 2222. This is an important, to me, a milestone order that will change basically how we do business behind the customer, in distribution markets and wholesale markets. I will not spend time on this slide. It gives you, you will have the slides, it gives you a kind of a history about the path that FERC followed since 2015 to come to this point today, with a series of other orders and technical conferences. Maybe some of you have followed these developments. A milestone order, for example, came out in 2018 about storage, Order 841. People who are in the storage business, I recommend them to read. We worked on that. Many ISOs now develop models how to integrate storage into the wholesale market. That's a very difficult asset to integrate because it can be demand and generation within 24 hours. It can do arbitrage. When do you charge? When you discharge? There is a lot of work that has been done here. Maybe this could be a topic for a future seminar. We'll not talk about this, but this is a game changer. And after that, there were a lot of technical conferences about DR aggregation. I will talk briefly about DR aggregation. This is fundamental to our business now. And now we have the FERC Order 2222, which basically, in a few words, it's a long order, hundreds of pages, but in summary, what it does, it creates the concept of DR aggregators. In California, we have DR aggregators since 2016 as an asset class and as a market participant. So you can register with a Cal ISO as a market participant. Now, this becomes the law of the land. Every ISO needs to create this separate market participation class. So DR aggregators aggregate assets at the edge of the grid. It can bypass, this is very important, bypass the distribution to go directly to the wholesale markets. DR aggregators could be large in geography. They can aggregate different types, different technologies, from IoT devices to solar, wind, distributed generation, CHP, whatever they want, storage, EV charges. And when you have a multi-node DR aggregator, DERA, then you need to give at registration to the wholesale market the distribution factors that, of course, are dynamic, they can change, and you need to update those. But the fundamental premise of the order is that it allows DRs to bypass the distribution system and go directly to the wholesale level. So we can have market transactions directly to the wholesale level, even though the flows, the physics, will go through the distribution system to the transmission system back and forth. As you see here, there is a gap between the physics and the economics, okay? So this bypassing, it can work economically speaking, but we need to make it work physically. The engineers need to deal with this. There is a gap in the whole process. So this gap translates to an intense coordination between ISOs and DSOs. What data will pass in what time frame, from all the way to planning and moving forward all the way down to the 5-minute real-time market. So a lot of issues have not been resolved here. It's an area of research. For example, I'm a DR aggregator. I aggregate 2 megawatts of assets. I bypass distribution. I submit my asset to the wholesale market to provide, for example, spinning reserves. Then the ISO sends me an instruction in real time to activate my asset to produce energy. Now, can you hear me?
Yes.
Okay. Now, the ISO can apply non-performance penalties if you don't activate your resources. But the DSO that has visibility of the distribution system due to congestion constraints at the DSO's level may override that instruction. You are still being penalized from the TSO for non-performing, even though it was not you that didn't perform, simply it was an override from the DSO. That's a simple example that gives you an idea of the problems we have in coordinating the DSOs for the ISOs. That's an open area for research. I've written a couple of papers on this, but it's really an area where more work needs to be done. What visibility the wholesale markets will have at the distribution level. Furthermore, this gives a lot of emphasis into the fact that the DSO, when it clears the markets, needs to have full visibility of the distribution system, which means we need to clear markets with all the transmission system in place, which means DLMPs. LMPs. Okay. I talk about this slide that basically we need to coordinate the ISOs and the DSOs in all time frames from technical and the market perspective. At the minimum, this coordination needs to take into account all these items I mentioned here, from congestion, voltage, grid balance, black start protection, islanding. It's a big list, and it's an open area for research. So, related issue, but extremely important, in coming up with models for the coordination between those entities is the governance of the DSO. When we say DSO, what do we mean? There is a minimum governance of the DSO or a maximum role for the DSO and many variations in between. I'll give you an example. Let's take the maximum role. The distribution companies in the US, we want to aggregate all the resources they have available and participate as the only entity into the wholesale market. So everything will go through the distribution company. And then, of course, the distribution company will provide revenues, will pay all the DR aggregators. In this model, the DR aggregators will be subjugated to the DSO or DNO if the owner is also the operating entity of the market. On the other extreme, we have the minimum DSO, which means the DSO has a platform to solve grid problems, but all the DRs, all the DR aggregators, can participate in this platform to solve distribution problems, or they can go directly themselves to the wholesale market. They don't need to go through the DSO. That's a minimum role for the DSO. Depending on the governance, different communication protocols need to be developed. Just to give you an idea, the Europeans are moving more towards a minimal DSO, which means all these DRs can go on their own way and have an unfettered access to wholesale and retail markets. Here, there was a pressure from DNOs to really be the only participant in the wholesale market. So all DR aggregators can go to the wholesale market through the DSO. Third quarter 2022 is changing that. It gives to the DR aggregators the ability to go directly to the wholesale market. Many states don't want that. There will be a lot of litigation, and I think this will be resolved in the courts because many states are basically accusing FERC for overstepping its bounds, okay, overstepping its authority. In all this process, one thing is clear, that when we solve distribution markets, we need to take into account the wholesale market price at the substation level. Okay, very briefly, in the next two slides, I talk about DR aggregation analysis. This is a new concept. We never published about this. Many people take it as granted. The only thing I want to say here is, I can form an aggregation that is good for the system, it is good for me. I can form another aggregation that is good for me, but not good for the system. There are a lot of things to talk about here. It's an open area for research. So we separate the aggregations in three categories. Fundamental aggregation, there's a complete consistency between what we call system benefit and private benefit. In other words, when the aggregator performs the aggregation, offers this capacity to the markets, there is a benefit to the system. And at the same time, it maximizes the value of the DRs and the revenues. There is a transitory aggregation where this happens to some extent, but not always. And there is a third aggregation. I call it opportunistic aggregation. It's not even a standard term in the industry. We have done some confidential work in Europe about this. Opportunistic aggregation is the type of aggregation that creates short-term benefits for the aggregator, but it's at the expense of the system. Just to give you a hint, how you do procurement on regulation, for example, how you allocate cost for balancing, how to aggregate, for example, EV charges in different parts of the city that are in different parts of the circuit, in different ends of a congested circuit, that may create a private benefit, but not a system benefit. So aggregation should not be taken lightly. This is another open area for research. What aggregations should be encouraged and what aggregations should be discouraged. Currently, the aggregators need to be registered with the ISOs, but I don't think the ISOs have tools when to approve or disapprove an aggregation. So as I said, we're moving to a multi-tier market now. On the left here, we have wholesale markets. These are some of the products. On the right, we have the distribution markets. These are some of the products. And on top, we have markets behind the meter. These are customer markets behind the meter. For the other two markets, you can have your assets in front of the meter or behind the meter. There is a model that is being developed. We call it revenue stacking model, where an asset in distribution or even behind the meter can participate to reduce the demand charge of the customer, so gets money from the customer. At the same time, you can use the same capacity, let's say you have a storage asset of 2 megawatts, to solve a problem in distribution, let's say relieve congestion in a circuit, and at the same time offer this capacity to the wholesale market to provide regulation. Same activity, same megawatts, 3 different markets. We strongly believe that this asset needs to be paid from all these markets. Again, as you understand, this is an open area. Many people, especially utilities, they are calling this double dipping or triple dipping. They are trying to discourage this. I believe that an asset, under some conditions, can participate in multiple markets for multi-revenue generation. But again, how this will develop, that actually the FERC 2222 is talking about this. Now, this is kind of another way to present similar concepts here. DR aggregators, on the right side here, you have a retail DR. They aggregate those assets. They create what we call virtual power plants, and they offer this capacity to the wholesale markets in different products: energy, ancillary services, energy arbitrage, long-term capacity. They play those markets. There is a lot of complexity behind the VPP construction, but this is dealt at the DR aggregator level. So the energy markets, they just simply see a simple point of connection. They deal with one entity for bidding and settlements and the registration, telemetry, and all the other things. Of course, if the DR aggregator gets an instruction, it needs to distribute that instruction to all these assets, okay? And to what extent now the ISOs and the DSOs will have visibility in all these assets, it's an open question now. The order is trying to put a threshold below which visibility is not necessary. And they're talking about maybe 5 megawatts. So another important area that we see changes over the years. On the left is how the markets are evolving, or if they have worked so far in terms of volume and in terms of revenues. However, as we move to a DER environment and what we call a zero marginal cost system dominated by renewables, then we'll have basically an increase of the value of ancillary services. How much increase, we don't know yet, but there will be additional services. For example, ramping up or ramping down as a separate service, primary frequency response as a separate service, and all the other flexibility services that not all ISOs have today. So there will be a substantial increase in the ancillary services world. Moving now to our specific development, how we see the DSO markets evolving. There will be markets similar like the ISO markets, day ahead, adjusted markets, hour ahead, or real time. This is a typical day ahead market horizon. The market will close at 10. It will, let's say, have a 24-hour horizon. Half an hour is the time interval. It will solve a MILP with a distribution power flow to produce price set schedules. This is a platform that the DSOs will have. In real time, we have something similar. We have 5-minute markets, maybe look ahead for a time duration of 30 minutes or more with an interval of 5 minutes. So between 10 minutes and 5 minutes earlier in the middle, it's a whole discussion why we choose the middle. We run the real-time market. The market solves in 2-3 minutes, and then we give instructions to all those DR assets from the interval 0 to 5, and we do the dispatch, and we provide the distribution LMPs. Now, in terms of development, we follow the similar approach, which is basically we overlay a MILP algorithm, mixed integer programming, on a distribution power flow. When we started this, we thought it was an easy thing to do, given our experience from wholesale markets. We have done this for 20 years, and we have built markets in many, many countries. That's not easy, though. The distribution power flow is very different. It's unbalanced and three-phased. As a result, we produce along the feeder 3 prices, one for each phase. Okay, 3 prices. And offers are coming in from DR aggregators that the market clears. And then there is an iteration between the MILP and the distribution power flow. The implementation, we keep it as flexible as possible. We allow self-schedules, which is consistent with the wholesale markets. We allow simple offers, price quantity, block offers, different type of complex offers, and bilateral transactions to comply with the European model, which is different than the US model. A lot of work here about how, because certain feeders may have enough DRs, but maybe other feeders don't have enough DRs. So a lot of constraints may be violated. So there's an intense use of slack variables with penalties in order to relax those constraints if we don't have enough economic offers. So moving on with the offer submission, in the distribution level, customers and suppliers submit bids and prices for generation and load for each phase, and also they can submit also VARs if they have smart inverters. We also have non-participating loads that we take based on profiles and metering data, and we use those as part of the clearing. And of course, we use the LMPs from the wholesale market at the substation level as input to the distribution clearing. In a high level, that's how it works. We start from an unbalanced, the second block on the top. We solve the distribution power flow. We check limits. If there are overloads, we come up with the shift factors. I have a paper how to do this in distribution from the factorized Y-bus metrics. Then we linearize those constraints and we pass them to MILP. And the MILP solves which units will be scheduled. And then after it's clearing, it solves an LP to produce prices. Now, it's important to note here that we group the constraints in 2 levels. The near violated, let's say 90 and above, 90% and above, and 90% and below. Here, we include in MILP only the near violated constraints, not everything because we cannot solve it. So we come up a subset of linearized constraints that are, let's say, 90 or 80% loaded and above, and of course the violated constraints. And we solve, and then we solve the distribution power flow again. We check limits, and we iterate this process a couple of times, and we solve. Once there are no overloads, we come up with the distribution LMPs. That's another picture how this works. We have on the right the physics, the distribution power flows. If we have half an hour intervals for the day, we have 48 distribution power flows. As I said, if we solve, we linearize with the shift factors, the PTDFs, power transfer distribution factors. We pass them to MILP. MILP solves and iterates. That's the high level process for clearing that market. I have some math here. There's a power balance equation, of course, that takes into account the transfers from transmission. We have a set of linearized constraints. We have a set of voltage constraints. We come up with the shift factors at the bottom, as you see, and we iterate, and that's how we solve this problem. Now, a few comments about the distribution power flow. We produce what we call the entire network up to the customer meter. We include phasing, the conductor capacity, the transformer type. All the individual phases are modeled. We include both radial and mesh systems. European systems are a little bit different, but below a certain level, all the systems are radial. The systems are imbalanced, of course, and asymmetric. We use the robust Y bus metrics. We looked at, of course, include the voltages for each bus at phase, and we calculate the flows, the conductor flows in kW amps at kVAS on its transformer. And from that analysis, we calculate all the list of overloaded network elements. Now, we enforce voltage constraints by adjusting capacitors, voltage regulators, and also kVAR injections. Now, the new smart, oh, I'm sorry, there's a typo here, smart inverters can source and sink reactive power. So there can be a control variable that participates in voltage control. It will be paid for that based on its offer. Now, we need to provide incentives to encourage installation of all these smart inverters because they can help a lot smoothen out the voltage profile down the feeder. And the dual variables that come up from the LP solution are calculated after we run MILP. Okay, we force voltage constraints using reactive controls, and we produce shadow prices. Now, there's a lot of discussion in the industry if we can use those shadow prices to price reactive power. And there are issues here because it's a local issue. We may have market power issues. It's not an engineering problem, it's an economic problem. Some people think that we should pay them only opportunity costs and not based on the shadow price. But so it's an open area for work, actually. With this slide, I want to make you sensitive to the fact I see a lot of efforts, especially from academics, to try to emulate the ancillary services from the wholesale market to distribution. This cannot work because the ancillary services in distribution are very, very different. For example, an important service is the transfer capacity constraint. One thing that is so different from distribution is switching operations. In order to develop a good distribution market, you need to understand how distribution engineers and operators deal with the problems today. So if you look what they do every day, they do so much more switching than we have in the transmission level. And one of the reasons they do switching is to reconfigure the conductor so they can meet the load from another source. This means that they need to maintain spare capacity at the tie points to allow those load transfers. This means additional constraints, and this is an ancillary service. To us, this is the most important ancillary service to allow capacity, spare capacity in certain feeders in order to allow those load transfers. So those constraints may become binding, so there is a shadow cost to those constraints, and that's how you price that ancillary service. So that gives you an idea of, we're talking about very different type of work that needs to be done to develop this market compared to the wholesale markets that many of us, have developed and designed over the years. Now, I'll talk to you about some problems we have. A key issue in distribution is lack of data. In transmission with ISO markets, this is not an issue. We have very good data. The transmission system is very well behaved. But in distribution, even with smart meters, we upload this data the next day most of the time, but we need real-time data for the real-time market, the 5-minute market or the 50-minute market. So there are communication challenges. We need different protocols and processes, but clearly data is a big problem. Also, non-participating loads are part of the clearing to set the fixed loads. Not every load, of course, can participate in markets. So how we deal with the smart data in order to solve the real-time market remains a big issue. We don't have this data on a 5-minute basis. In the next couple of slides, I'll present the best, I think, DR scheduling use case related to feeder reconfiguration. Today, the distribution companies, the DNOs, perform multi-tier feeder switching, okay? Cascaded feeding switching in order to adjust the feeder loads. This is done though heuristically, if they want to move loads to another reconfiguration. Distribution engineers have been writing papers on reconfiguration of distribution grids for 20 years. So there are plenty of literature on this subject. What is new though is how this now is affected by the DR markets. So even the existing models don't work well. They are heuristic because we have multi-layer transfers. The DNOs just basically use judgment. They don't use optimal plans based on clearing of markets to come up with optimal multi-layer transfers. So what we have done, we have updated our platforms to develop optimal switching plans in coordination with the DR markets. What is missing is the coordination of those switching plans with the DR markets. So for that, you need basically powerful mixing reserve linear program methods to explore all these switching options, choose the optimal ones that you will use once you have exhausted the DR scheduling. In other words, to do load switching, switching options, execute those, this should be done after you have exhausted your DRs. So we use weights for that. We minimize the number of weighted switching actions. We have the cost of DR schedules. All these costs go to the MILP, and of course we assign weights also to switching action. You can do it remotely. Many DSOs have now, DNOs have, you can do this remotely. So this methodology basically produces multi-tier plans with cascaded transfers, but activates the switching operations only if you have exhausted the DR resources. So if you still have overloads in different circuits and you don't have enough DR resources, for example, enough storage or demand response that you can activate temporarily to solve the circuit, an overload, then you deploy the switching plan to meet the load through a different configuration. And that's how we implement it. That's how utilities tell us is the right way to do it. Now, I'm almost at the end. If you give me 5 more minutes to tell you some of the concerns we have. Again, availability of network data. I mentioned this. Many utilities, of course, they use GIS data to extract all this data, add data from the DMS. from various feeders above the 11 kV level, for example, we need metering data, but on a 5-minute basis, not or 15-minute basis, not for the next day. And we need, of course, to develop load profiles for non-participating loads. So we're talking about a lot of data, but I mean, this is the engineering part, right? But there is the economic part that as market designers, we're very much concerned about. Because the feeders are radial, okay, it's not a mesh network as we have in transmission, where you can resolve a constraint in transmission from multi-paths, from many PTDFs, from many offers. Here, you have to deploy the assets along the feeder, the DRs along the feeder. So if a circuit along the feeder becomes congested, we have noticed that the DLMPs are very volatile. All the DLMPs below that circuit, they can hit the cap. They are very volatile. They are not smooth. And a lot of work needs to be done how to smooth those prices. A related issue is market power. Where do we apply these market mechanisms? There is a penetration of DRs is happening. It will be happening in the future, but we don't advocate to those to utilize markets in the entire distribution system where you may not have DRs. So we need to start from subsets of the system where you can have enough DR participation to deal with market power. Market power is a big deal in our business. We have spent half of our career basically develop market power mitigation methods. This is a problem in distribution too. It will be less as more and more DRs appear in the market, but it's an issue. The other issue is still there is some work that needs to be done for the loss component of DLMPs coupled with the slack formulations. Okay, these are some of the issues. As I said earlier, the FERC Order 2222 will probably be challenged in the courts by certain states. I believe that we need to provide price incentives to develop additional products related to voltage issues to encourage smart inverters all the way down to the feeders to improve the voltage profile. We need to improve the smart meter infrastructure to provide real-time information to the markets. Scarcity pricing during restoration after a fault is a problem. Scarcity pricing is a problem even today in the wholesale markets. In most markets, it's an administrative thing. ERCOT is one of the markets that has very advanced scarcity pricing. As I mentioned, market power is a big problem. And to close this, coordination of DR markets with ISOs remains an open issue. There's a lot of work is being done there. I will close with this slide that the action clearly has shifted to distribution from the wholesale markets. LEM is what we call local energy markets. DRs are emerging, and now the regulatory framework is being developed. It is evolving at FERC and at the state level. I personally advocate unfettered participation of DRs, DR aggregators in all markets, in all multi-tier energy markets, in order to maximize their value. We don't like subsidies. Subsidies need to be phased out. Now renewables can compete on an equal basis and in many markets are cheaper than gas power plants and other fossil power plants. So we need to reduce or eliminate the DR perverse incentives. And I will close with an item that it's obvious to engineers and academics, but not to many policymakers and regulators, that the location is important. We need to include the distribution network in as much detail level as we can, include distribution constraints in order to reflect locational effects and capture the true value of DRs in the system. Thank you.
Thank you, Alex. That was great. So we'll open it up for questions. And I think we have about 20 people on the thing. So go ahead and just unmute yourself and ask the question. I think we'll try it that way before we try to if it goes unstable, we'll try to control the conversation. Anybody?
Alex,
I see you, so go ahead.
This is Gary with Burns and McDonnell. In this marketplace, who performs distribution planning, and is there collaboration on the distribution planning side between the transmission system operator and the aggregators?
Distribution planning clearly is a domain of the DNOs, the distribution network owners. They will be doing the planning. In many distribution systems, we have temporary congestion, but many circuits have plenty of capacity. Maybe they are overbuilt. So planning will remain the responsibility of the DNOs. Now, as I said earlier, the DSOs could be the same company like the DNO. In other words, a distribution utility could be the DSO, but there are definitely market forces that they are asking, pushing for a DSO to be a third party, separate from the DNOs. It's basically the ISO concept in the US. The transmission owners own the network, but the ISO operates the network. So there is a communication, of course, a coordination between the DNO and the DSO, if that's a separate entity, in terms of the outages, changes, and so on that need to be passed. Same way that we do in the US between the coordination between transmission owners and ISOs to manage the outage. So there is an outage coordination issue. All the ISOs have managed that. So there is a coordination. And of course, the third pillar in this equation is the coordination with transmission. Even though I think these are different companies that deal with different parts of the grid, there should be some coordination, especially as we move forward, where DR assets in distribution will bypass distribution to offer services to the wholesale market. There is an open issue to what extent ISOs will have visibility to distribution constraints. FERC Order 2022 does not fully address this issue. There's a communication gap, but clearly it says that the aggregators are responsible for non-compliance from an ISO instruction if they are overridden, if that instruction is overridden by a distribution company because of security problems in the distribution grid. So it's an open area to what extent there will be a coordination, but in what form and shape between ISOs and the DSOs is an open issue.
Anu, go ahead and ask your question instead of my reading it.
Sure. Yeah. Hi, Alex. This is Anu Anuswamy from MIT. It's a great presentation. In fact, as I was looking at many of your slides, I was thinking, good part of these things could have been something that I would have given a talk on, because recently my student and I shared our paper on a retail market. And again, we can have a discussion about that offline, but it's really great to see many of the points that you're making as to why a retail market is needed. But I do have one specific question. I mean, in addition to FERC providing a pushback, I mean, all the ISOs, someone at PJM is going to say over my dead body type of a thing, for these DSOs. So what do you think is the biggest argument that supports this retail market development and this large penetration of DERs? Is it a demonstration of this coordination gap that you're talking about? I mean, how do we make this? What do you think will make this happen?
Okay, the key obstacle for the development of the retail markets is the misalignment of incentives. I had several slides on this, but I took them out because I would go beyond the 1 hour. But here's the issue. In the US, the owners of the grid in transmission and distribution make money from capital investments, from CapEx. So the more money they invest, the more money they make. So they are not in the business of saving money, because the rate design, the way it's structured today, is based on CapEx. Now, this is changing. The DR markets basically are for better utilization of existing assets. If I have a distribution circuit that is violated, let's say 100 hours a year, now what utilities are doing, they are upgrading a transformer, they spend $1 billion. In the future, we'll use DR assets, storage, demand response, and other assets to shift the usage for those hours and not upgrade the grid. So the retail markets, the essence of those markets is what we call to provide non-wire alternatives. I use the term that New York is using extensively, non-wire alternatives, NWA. So, but for that, we need to align to provide incentives to utilities to make money from saving money. Mm-hmm. There are some utilities in the East that are experimenting with this. That's why European markets are much more advanced in distribution, because they have what we call performance-based regulation for 20 years. Let's take, for example, England and many other places. So you make money by saving money, and some of the savings will flow back to the ratepayers, and some will flow back to the shareholders. So if I'm a utility that I make money only from CapEx by investing, I don't want these markets because I don't make money from these markets. So to me, the most important obstacle, aside from other maybe technical issues or economic issues that will resolve from market perspective, the key issue is the business issue to realign the incentives for utilities to embrace those markets and make money from saving money, not only from CapEx.
Okay, thank you.
Okay.
So Alex, let me ask a question. You obviously, in the way you're handling the distribution system, you're expecting to take into account the constraints of the distribution system itself, which 2222 kind of avoids and goes, let's say, aggregator go directly into the wholesale market. But given that, my question is this, especially since you suggested that there may be some topology changes you might have to make in the distribution system to make the markets work better. And so my question is that the aggregator market seems to include things that are on the customer side of the meter, which Correct. At this time, there is no visibility from the DSO. So the question is, how do we make sure that the operator, the DSO, is not completely blind to what is happening on the customer side of the meter, because in terms of what the bidding is taking place, how the market is being cleared, and so on.
Yeah, that's an important question, and many utilities are struggling with this issue. There is a point that the DR asset needs to be clearly visible to the DSO for many, many reasons. The question is, it's a threshold question. FERC somewhere says that the threshold could be 5 megawatts. In the ERCOT market, they are talking about in specific utilities, like in San Antonio, that we're doing some work. The limit, the threshold is 2 megawatts. So every jurisdiction will come up with a threshold below which you don't need to have visibility. But if you exceed the threshold, you fall into a different category. You have different metering requirements. You have different reporting requirements, and the DSO has to have visibility to that asset. So, of course, this will change as more and more DRs appear in the system. For example, in California, behind the meter for rooftop solar, the ISO does not even know how much rooftop solar we have. We may have thousands of megawatts behind the meter rooftop solar. This affects the system. So there are all these issues now. If you pair this with storage, which happening in many customer locations, you develop what we call hybrid virtual power plants, hybrid plants between solar and storage. To what extent you charge or discharge? Are you going to be totally free to do arbitrage? And at what point you need to be visible to the ISO market, let's say, let alone to the DSO market? And it's a threshold question again. I believe that it will be in the order of a few megawatts, 1 or 2, max 5. But again, these numbers will change as more and more DRs, penetrate the system in that level.
So follow-up question then is, I understand what you're saying about the threshold. The problem is that the aggregator doesn't have to many pieces of DERs, and they may not. They may be next to each other, they may be in the same place, or they may be in different feeders altogether. So the threshold has to be on individuals or on the aggregator.
Right now it's on aggregation level. And this goes back to the few slides I had about types of aggregation. This is an open area for research. As I said, they are fundamental aggregations that the private interested private value coincides with the system value. They're on the same direction, but there are other opportunistic aggregations where aggregators can play games and to their benefit at the expense of the system. So there will be a point where the DSOs will say, no, I cannot allow this aggregation. Right now, for wholesale market participation, FERC Order 2222 is explicit that during registration, you have to register your aggregation, and you have to submit your distribution factors from your asset to individual entities. But the ISO does not see beyond the point of the DR aggregator. The DR aggregator has to activate all these assets if there is an instruction for an ISO, for example. Now, there are a lot of issues here about conflicting instructions. Maybe some assets are increasing, some assets are decreasing. So there are a lot of issues about settlements and about following instructions. Currently, the ISO says, if I give you a 2 megawatt instruction and you respond to the 2 megawatts, I'm okay. I just want to see as the net 2 megawatts what I gave you. What happens behind me? How do you allocate that? It's not my problem. But eventually, it will be the problem of the DSO because some of those allocations may violate circuits. So there are issues that need to be resolved in terms of coordination. But now that's the level of knowledge we have, or that's to the extent of regulation we have. The instruction will go to the local DR aggregator, and then it's up to the DR aggregator how we'll activate that instruction.
Okay, so I have a peer about the approximation needed in linear programming that you're using, because if you have an unbalanced distribution system, what kind of approximations do you need to make to
Yes.
to do linear programming?
Great question. Great question. Our fear is that the more DR penetration takes place, the more asymmetric the distribution system becomes. So we believe that DR penetration in the distribution level will create some challenges to the distribution operators and some challenges to us as market designers and programmers, because they may create more asymmetries in the distribution network for clearing. So again, this was one of the first developments. More work needs to be done. I think now we know how to do wholesale. There is a lot of work that needs to be done on retail.
Another question came in written. In a multi-tier market, who leads and who follows?
Leads meaning, I'm not sure I understand the question completely, but these are what I call unfettered markets. The ISOs lead the wholesale market, the DSOs lead the distribution market, and we have markets behind the customer. There is a coordination between the two, but no one is leading everything. Everyone has a specific jurisdiction. The DSO has no jurisdiction on ISO, and the ISO has no jurisdiction on the TSO. So there will be coordination issues. It still remains an open issue in all time frames, but these markets are being developed independently of each other. And there is a SIMS issue at the border. For example, wholesale prices will be used as an input to distribution at the substation level at the T&D interface.
Yeah, I think that's really was the what was being asked, is that you're using the transmission level LNP as a constraint on the DLMP.
Yes, it's an input, but
yeah.
There are many companies in the US where they don't want to go into the level of distribution markets, and they say, I use the wholesale market LMPs, and I will add a scalar, a proxy number, to take into account distribution losses and congestion in distribution system.
Okay.
That's it. So, but basically there is one market. It's simply the LMPs are augmented with a scalar. We don't like that. Because now you subjugate the distribution markets to wholesale markets. For the distribution markets, you need to have your own platform. You have DR aggregators. You have all these assets at the end of the grid. And they produce offers, and they will clear their own markets.
Okay. All right. I think we're hitting 12:30 here, so we'll probably bring this to a close. Thank you very much, Alex. We're looking forward to this presentation, and at least you tell us that there's lots of challenges ahead.
There are a lot of challenges for you academics to be involved and help the industry, no question about it.
Yeah. Okay.
Thank you very much to all for your time.
Thank you. Thank you. And I'll bring this to a close then.
Thanks, everyone.
Brenna, you're shutting down, right?
Yep.
Okay, thanks.
Have a good day.